Reinforcement learning has become a cornerstone for aligning large language models with human preferences and enhancing their performances on complex reasoning tasks. However, a critical challenge still persists. How can reinforcement learning be effectively applied to tasks at inference time where ground truth labels are not available? One effective strategy to address this is called test time scaling, an idea about leveraging increasing computational resources during inference to increase reasoning quality. By generating multiple candidate outputs and aggregating them through a mechanism such as majority voting or weighted scoring. Another idea comes into mind is test time training. It refers to updating model parameters based on input seen during inference. When combined with reinforcement learning, it offers a pathway to adaptation without annotations, which is a powerful step towards generalization. But a challenge comes in. How do we estimate the reward? How do we evaluate performance without labeled outcomes? Now, this is where a new paper from Tsinghua University comes in, and they propose a method called test time reinforcement learning. Let's say you have a prompt. What is 1 plus 1, you say? Now, feed that prompt into the LLM, and the LLM produces a main output. Given that you can set the temperature of the LLM to be greater than 0, you can then tell it to generate multiple different sample outputs given the same initial prompt. Using all these different sample outputs, you can now perform majority voting to get the aggregated final consensus output by selecting the most frequently occurring prediction among the outputs. Now, this final consensus output is then used as a pseudo label for the optimal action. You then compute the reward function given the main input and the consensus output, such that high reward is only assigned for cases where your main output matches the consensus output exactly. In this case, that would be 0. So the main mission is essentially to maximize the expected reward and update the LLM using gradient ascent. I myself am pretty surprised at how simple this approach really is. It seems to me that this approach could improve the LLM's accuracy, but only up to how accurate the majority voting system is. But hell no, because I was wrong. In fact, this approach not only surpasses its own pseudo labels, but in some cases approaches the performance of where the models are being trained on the test set itself. This establishes a self-improvement loop, refining its outputs through reinforcement learning on its own generated predictions. For instance, take a look at this. Qwen 2.5 will math 0.5 billion parameters, improve from 33% up to 80% of accuracy on Math 500 benchmark. That's a 142% gain of improvement, despite having no truth labels behind it. Isn't that crazy? And the reason behind why it works so goddamn well is that despite majority voting having its obvious flaws like being noisy and having incorrect signals, these flaws are used as negative reward signals, which helps the reinforcement learning algorithm to improve the large language model. However, there's a few caveats behind this approach, and one of them being that it only works well if your LLM is at a certain size, somewhere around 7 billion parameters or higher than that. So size does matter.
I've been thinking about a way to integrate the troll method with our existing project, and it could lead to some really interesting results. Use troll to create an ensemble of models, each trained on different aspects of the data. The single labels generated from each model could then be used to refine our hypothesis and guide our research in a more targeted manner.